For decades, DFT has had a very clear center of gravity. Make the design testable, generate high-quality patterns, and close structural fault coverage. That foundation is not going away. But as silicon becomes more software-driven, more hierarchical, and more operationally complex, the boundary around the DFT problem may be changing. In this presentation, we'll look at several findings from the 2026 Siemens and Wilson Research Group Functional Verification Study and what they suggest about how DFT is being verified and used today. The question behind the data is simple. Is DFT still primarily about structural test closure, or is the evidence it produces becoming relevant to a much broader silicon assurance problem? The important point here is that the foundation of DFT has not changed. Structural test, ATPG, scan, memory test, and fault coverage still matter. What has changed is the environment around them. Test modes now interact with clocks and resets, power intent, hierarchy, security policy, embedded processors, firmware, and increasingly multi-die systems. And those interactions continue into in-system test and post-silicon debug. So a design can be structurally complete from a traditional DFT perspective and still carry system risk if these behaviors are not understood before silicon. That expanding boundary is the context for the survey findings we'll look at next. Before we get into the individual numbers, there's an important point about how to read this data. This is a current state view. We don't have historical DFT trend data here, and no single percentage proves that the industry has moved to a completely new operating model. What is interesting is how the findings line up. Verification is happening earlier. DFT appears to be more integrated with mainstream verification. Ownership appears increasingly shared. Scale is putting pressure on execution. And functional content is starting to appear as another source of defect coverage evidence. Any one of those findings is interesting. Together, they suggest a broader shift. So with that framing, let's start with the first signal, when DFT verification actually begins. The first signal is timing. Nearly 39% of respondents say functional verification of DFT-related logic begins before RTL freeze. Another 44% begin after DFT insertion at RTL. Taken together, that means 82.9% begin by the post-insertion RTL stage. I want to be careful not to overinterpret the exact milestone sequence, because insertion can happen at different points in different flows. But the broader message is clear. Most teams are not waiting until ATPG and final pattern validation to begin building functional evidence around DFT. That can include things like clocks, resets, test modes, access paths, power interactions, or validating the actual inserted logic while debug is still less costly. So the takeaway is not that everyone has adopted the same shift-left methodology. It is that DFT verification is increasingly being treated as a pre-ATPG functional responsibility. The second signal is integration. Nearly half of respondents describe DFT and verification as fully integrated through shared environments, coverage, and regression. Another 42.6% report partial integration. So in total, 91.9% say the two are connected in some form. The important point is not that every team uses the same coverage model or the same execution flow. The survey does not prove that. What it does suggest is that DFT verification is increasingly being performed inside the same verification infrastructure used for broader functional work. And that makes sense when test modes affect clocks, resets, memories, power states, security access, or firmware-controlled diagnostics. Those interactions are difficult to validate if DFT and functional verification remain completely separate. So the takeaway here is that integration is becoming less of an exception and more of the normal operating context. One important point up front, these were multiple response questions, so the percentages overlap. They are not meant to add to 100. What we see first is that specialized teams still matter. About 61% report a dedicated DFT or test team, and nearly 53% report a dedicated functional verification team. But alongside that, 46.4% say the functional verification team is responsible for validating DFT logic, and 43.8% say responsibility is explicitly shared between teams. So this is not a story about verification taking over DFT. It is a more matrixed model. DFT specialists continue to own areas like architecture, insertion, ATPG, and structural coverage, while verification teams contribute environments, assertions, regressions, and system-level scenario validation. The key point is that specialized expertise remains, but the infrastructure and evidence are increasingly shared. The next signal is scale. What is striking here is how closely the leading challenges cluster. Long run times, limited visibility and debug, hierarchical complexity, and lack of reusable verification infrastructure all land near the top. These are not really four independent problems. They compound one another. As designs become more hierarchical, there are more boundaries, more configurations, and more contexts to validate. Pattern and gate-level simulation become expensive. Scan compression and BSAE can make behavior harder to observe. And without reuse, teams end up rebuilding verification and debug infrastructure at each level. So the challenge is no longer simply generating test content. It is being able to execute it, observe it, debug it, and reuse the verification approach at system scale. And as integration moves beyond a single die, that scale problem becomes even more pronounced. Scale becomes even more challenging when we move beyond a hierarchical SoC into chiplet-based and 2.5D or 3D assemblies. Now, DFT has to work across more than one level: core, die, package, and sometimes board. That brings in known good die tests, die-to-die interconnect test, package-level access, retargeting, and post-assembly diagnosis. The key issue is that the evidence chain becomes more distributed. Test data and diagnostic responsibility may cross suppliers, security domains, and lifecycle stages. So this is not about structural closure becoming less important. It is about having to establish structural closure and connect the evidence at multiple levels of integration. And that helps explain why portable access, retargetable content, and lifecycle-aware test architectures are becoming much more. So how are teams dealing with the scale pressures we just discussed? Gate-level simulation with patterns is still the leading validation approach, selected by just over 54% of respondents. But the number I find interesting is the 38.3% who identify emulation or acceleration-based validation as their primary approach. We should be careful with that number. This is not a hardware emulator adoption statistic. The survey category may include hardware emulation, simulator acceleration, multi-core execution, specialized DFT-aware engines, or other accelerated methods. So I see this less as a technology market share number and more as a signal of scaling pressure. Long test sequences, repeated initialization, full chip patterns, memory test validation, and software-controlled diagnostics all create execution demands. Gate-level simulation remains central, but more than a third of respondents are telling us that conventional simulation alone is not always enough to meet those demands. And the next finding may be the most surprising result in the entire DFT dataset. This is probably the most surprising finding in the DFT data. 77% of respondents say they fault-grade functional patterns to top off defect coverage, not covered by structural scan. Another 20% use functional pattern fault grading to verify structural scan at the IP or block level. And only 2.6% say they do not fault grade functional patterns as part of the DFT flow. Now, there is an important caution here. The survey did not define exactly what respondents considered a functional pattern, which fault models they graded, or how frequently the practice is used. So this is a strong signal, not proof of one uniform methodology, but the direction is significant. Functional diagnostic and software-driven content is increasingly being measured for the defect coverage it contributes. That does not replace structural ATPG. Structural patterns remain the controlled and repeatable foundation of manufacturing test. What is changing is that functional content is becoming another measurable source of silicon quality evidence. And once we start connecting those different evidence sources, the DFT story becomes much broader than structural closure alone. This is really where the findings come together. The important point is that structural DFT closure remains the foundation. Scan architecture, ATPG, compression, memory test and repair, access, and modeled fault coverage do not become less important. But that structural foundation now connects to other evidence sources. Functional verification asks whether test modes behave correctly with clocks, resets, power, X behavior, and system integration. Software-driven diagnostics exercise how test mechanisms are configured, invoked, observed, and recovered from. And in-system and field learning can expose new scenarios that feed back into implementation and pre-silicon verification. Safety, security, quality, reliability, and lifecycle policy cut across all of this. They both consume the evidence and place constraints on how DFT can operate. One caution is important. DFT evidence does not establish system assurance by itself. The opportunity is to connect these evidence sources and preserve the feedback between them. That is how DFT contributes to broader confidence in manufactured and operating silicon. And that brings us back to the central thesis of the paper. The foundation of DFT is not disappearing. The boundary around its role is expanding. So what do we take away from all of this? The data does not suggest the end of structural test. Scan, ATPGE, compression, memory test and repair, diagnosis, and fault coverage will remain essential. What the findings suggest is that structural test now operates inside a broader silicon lifecycle and system assurance problem. That is why we see DFT verification moving earlier, becoming more integrated with mainstream verification, sharing responsibility across teams, scaling through accelerated execution, and measuring the defect coverage contributed by functional content. The question is no longer only, is the design structurally testable, and have we closed ATPG coverage? The broader question is, have structural test, DFT behavior, diagnostics, software control, lifecycle access, and assurance evidence been connected well enough to support confidence in the manufactured and operating silicon? Meeting that expanded responsibility also changes what the verification flow must support. It requires connected evidence from RTL insertion and static analysis through scalable pattern simulation and fault grading to hardware/software co-verification for in-system test. The goal is not simply to accelerate final pattern sign-off, but to preserve evidence and feedback across the silicon lifecycle. So the conclusion is simple. DFT is not leaving its traditional role behind. Its role is becoming more consequential because its structures, behaviors, and evidence now operate across more of the silicon lifecycle.